Now we're going to discuss logarithmic functions, but a very particular one. So we talked about exponential derivatives, and we started just basically with one of them, one base, e. And now we want to do the same thing with logarithmic functions. So hopefully you remember from before that logarithms work this way, that if you have log base b of x equals y, that's the base, that's the exponent, that's the value. So it's b to the y equals x. If you understand that, then we're going to introduce you to log base e, which is the natural logarithm. So it's ln x. And I think we talked about this before last year when we talked about logarithms, but if not, all we're going to do is we're going to say we're going to look at what happens when we have base e. And that has its own name. It's called the natural logarithm, or ln of x. And you'll notice on most calculators that it has a log button, which is base 10, and then it has a ln button, which is base e, and it's used frequently. That's why it has its own button. We use it in calculus because it has a fairly nice derivative. So I'm going to show you that. But if you think about log base e of x, or ln x, equaling y, then that means that e to the y is equal to x. Okay, so ln of e is 1 because, again, that's log base e, so e to the 1 would be e. And ln of 1 is 0 because e to the 0 is 1. So I want to know, in particular, to start, what's the derivative of ln x? Okay, we're going to look at every base. We're going to generalize this, just like with exponentials. We're going to generalize it to things other than just base e, but we're going to start with base e because it's simpler. And so here's the derivative. The derivative, d by dx of ln x, is 1 over x. That's the derivative of ln x. The question is, how do I show that? How did I get to there? And typically, when we're proving derivatives, we've gone back to the limit definition of the derivative. But here, we're going to use the fact that the derivative of e to the x is e to the x, and we're going to try to then find the derivative of ln x that way. So we're going to say y is equal to ln x. We're going to rewrite that in terms of e. So e to the y is equal to x, and then I'm going to take the derivative. Okay, so we say e to the ln x is equal to x. You take the derivative. The derivative of x is 1. The derivative of e to the ln x is a chain rule. It's e to the ln x times ln x prime. This is what I want to know. What is ln x prime? Okay, so I'm going to then solve for it. So ln x prime is 1 over e to the ln x. And you remember from up here, e to the ln x is equal to x. So we replace e to the ln x with x, and that's how we end up with the derivative of ln x being 1 over x. All right. So fairly simple derivative, and that's why we like to use it in calculus. You probably haven't seen much of ln x up to this point if you've seen any of it, because it doesn't really advantage you to use it if you're just doing basic logarithmic calculations or solving exponential functions. But with calculus, whenever we want to do anything with logarithms, we're going to use ln because it has a simpler derivative than any other base. So again, we're just going to practice this to show you some of these. If I say, what's the derivative of x ln x? Okay, then I say, okay, well, y prime, that's a product rule. So the product rule says take this first function, multiply by the derivative of the second. So now the derivative of ln x, 1 over x, plus the second, which is ln x, multiply by the derivative of the first, the derivative of x is 1. So I end up with 1 plus ln x because these x's cancel. So that's my y prime for that one. All right. What happens if I ask you to differentiate ln of x cubed plus 3x plus 1? So that one, it becomes a chain rule. So the first part of the chain is the ln. So ln of whatever this is, the derivative of that is 1 over the whatever. So it's 1 over x cubed plus 3x plus 1. And then we multiply that by the derivative of x cubed plus 3x plus 1, which is 3x squared plus 3. And that's our derivative. And we could write that if we wanted to make it look more like one fraction. We could write it like this. All right, so that's my derivative of that one. What if we mix in a trig function? So I say, what's the derivative of ln of sine x? So I say, well, again, the derivative of ln first is 1 over whatever the argument is, and in this case it's sine x, so it's 1 over sine x, and then we're going to multiply that by the derivative of sine x, which is cosine x. And that actually simplifies to cosine x over sine x, and if you remember your trig identities, you know that that is actually cotangent x. So that is my simplified derivative. We have not been simplifying up to this point because we've just been trying to make sure you know the rules. But if it's a simple simplification, like that one was, then we'll do it. All right, what about something like this? So here's kind of a mess. We have cosine x, and then we have ln of all that stuff. Whoa, a little aggressive with my erasing here. So the question is, how do I do this? Well, it's a product rule. So I'm going to start with, there's my first function, there's my other function. So f prime of x is going to be, first of all, the first function cosine x multiplied by the derivative of the second. Now this is a chain rule, the first part of which is a power. So I'm going to go 3 onto ln of x plus 2 squared. Then I'm going to multiply by the derivative of ln, which is 1 over whatever the function happens to be. In this case, it's x plus 2. And then I would multiply by the derivative of x plus 2, but that's just 1, so I don't have to. Then I go plus the second function, ln of x plus 2 cubed. I'm going to multiply by the derivative of cosine x, which is minus sine x. And there's my derivative. I'm not going to try to simplify that. So hopefully that makes sense. Okay, now I'm just going to take a moment to just say, if you know that ln x is base e, then you can get a different definition. I'm not going to spend much time on this, but you can also define e this way, all right? And you don't need to know all of what's going on, but essentially what we do is we say f prime of 1. We know f prime of 1 is 1. So we say, what's the limit as h approaches 0 of f of 1 plus h minus f of 1 over h? And assuming that ln is our function, we get ln of 1 plus x minus ln of 1. Ln of 1 is 0, so you end up getting ln of 1 plus x over x. Because of the rules for logarithms, we're allowed to then bring the exponent up. And so what we end up with is a statement that looks like this. The limit is x approaches 0 of ln of 1 plus x, the 1 over x. And we say, well, the ln itself, this ln is not actually affected by the limit, so we're going to take it out. And so we end up with this. And so we know the ln of this thing, whatever this is equal to 1. And so that means by definition then that e is this. And that's actually how they generate, or how mathematicians generate e. We just keep plugging in smaller and smaller values for x and seeing what that limit approaches. So that just gives you an idea of e. As another idea, it doesn't really matter if you know where e comes from or not, but it's just something for you to see. So I'm going to get you with these two videos, with the ln x and with the one previous to this. You should be able to do the questions out of your textbook that have to do with exponential derivatives and logarithmic derivatives. And then what we're going to do is we're going to say, okay, now what happens if I don't have base e? So both of these, e to the x and ln x, depend on base e. What happens if I have some other base, any other base? And we'll talk about that in our next video.